Hi guys, welcome back to the channel. In today's video we're going to be taking a look at the new 24 volt pixels which will be arriving in the market in the not too distant future. So what can we say about them? What are they good for? And we need to then compare them to other pixels, particularly bullets, that are available currently. So we're going to do pixel wars. We're going to compare them with 24 volts, with 5 volts, 4 wire 12 volts, resistor 12 volts, and last of all, regulated 12 volt pixels. So let's see who will win. So I've been sent these 24 volt pixels as samples. Now the supplier has asked to be held anonymous at the moment because these are not yet available on the retail market. They will be in Q2, I believe, of 2025. So a couple of months time, hopefully 2 or 3 months, something like that. And they'll be out and then there'll be advertising, etc. So you're going to find out where they're coming from at that point. So what makes a 24 volt pixel different? Well, these are native 24 volt, so there are no banks of resistors or a voltage regulator on the back. This has typically been a problem in the past because people have tried to make them, but the amount of current drop, the amount of voltage drop down from 24 down to the 5 volts needed by WS2811 has meant that too much heat is being generated and it just doesn't work in the regular pixel format. So these guys have got around this. They have a brand new IC, integrated circuit, which is native 24 volt. So the circuit itself, the IC, takes a 24 volt input and it is then dropping the power down to the 1 to 2 volts needed by the LEDs. Now, I'm going to take a stab and say it must be using pulse width modulation for that because there's no other way it could be dropping the voltage down. The only other components I can see on this board are a resistor and a capacitor, and that is typical of the standard connectivity between pixels that you see on all of the other boards. Notably, the 5 volt board has these as well, and we know that they don't run resistors or regulators. Now I don't know the number of the IC, the model number or manufacturer yet. On this sample, all of the ICs have had the backs of the chips painted before they've been encased in epoxy, so they're not giving anything away. But what we need to do is we need to test them. We need to see what the voltages are really like, how much current draw there is on these pixels. So I've got my trusty multimeter to measure current and voltage. I want to measure the amount of light that they're producing to see how they compare. Are they as bright as our regular pixels at various brightnesses on a controller? So for the controller, we're using our trusty Baldric 8 because this controller will run on 5, 12 or 24 volts. So we can natively play with that. We're measuring the amount of light using our little lux meter here, and I've 3D printed a little adapter which sits on top of the sensor, and then we can stick the LED in it so that we can measure the LED on its own and not the ambient light in the area. And then finally, we're going to measure the amount of heat being produced by these pixels when they're up and running, and they have been for about half an hour. So I left all of the pixels running for half an hour on 100% brightness and measured the first pixel in the string with my little infrared camera just to see what it was producing, how much heat, and whether it's therefore being quite wasteful or whether it's fairly efficient. And last of all, I've done some statistics between the amount of power being consumed in watts and divided that by the amount of illumination in lux, and that gives us an arbitrary value which we can compare to see which pixels coming out top, which are most efficient and which ones are not. So there we go, that was a mouthful, got all that out. Let's start with the fun bit. So to give us a benchmark, I've started with the old favourite, the 5-volt bullet pixel. Now these things have been around since the beginning of time, I think. I'm pretty sure that when Christopher Columbus set sail from Europe to go and find the Americas in the first place, he had some 5-volt pixels on there as navigation lights. They are that old. But they're old and bold, and we know that they're good. So let's look first of all at the brightness of these. So if we take a look at this chart, we can see that as I increase the brightness in the white test mode on the controller, we've got a very steady increase in illumination. So we're starting down at under 2000 lumens and we increase up to pretty much 14,000 as we go. So a nice steady ramp. And as we move across to the measurement of watts per pixel, we can see that the current draw is pretty much a straight line. It's got a very slight bow in it, but as we'd expect, a nice line there where it is increasing with the amount of brightness being output. Now to keep this on a level playing field across the board, I'm using watts as my current reference. So watts, of course, is the number of volts multiplied by the number of amps being consumed. So I measured in amps on my meter, and I then divided that by the voltage that I measured going into the board to give us the wattage. And that way we've got a level playing field that we can plot all of the pixels on to see how they're doing. So there we go, a lovely uniform increase there in watts per pixel on the 5 volts. And then last of all, we've got the efficiency. So lower is better on this scale. So these things are getting more efficient, very slightly, as the brightness increases. But a pretty steady slope there. I mean, it's not got a huge angle on it at all, is it? So that's quite good. So well done, 5 volts. The last measurements then for the 5-volt pixels, we're looking at the amount of heat being generated by these pixels. So as we can see here on the thermal image, the maximum amount of heat generated by these was about 33 degrees C. Ambient temperature in here at the time was about 19. So that's an increase of about 14 degrees C over ambient. Now the gotcha, of course, on these is that because they're only 5 volts to start with, it doesn't take a lot to drop that voltage down, and you'll see the colours degrade as it goes. So running at 30% or so, you're going to need to power inject every 100 pixels or so. So that's the downfall of the 5 volt. But how efficient are they? How do they compare on brightness with the others? And how thermally efficient are they? Let's move on and find out. So the next ones up are at 24 volt pixels. So these nice shiny new ones. Now this is the output brightness. So how bright they are in comparison to the 5 volts. And you can see once again we've got a steady line as the brightness increases. But these are not as bright as your 5 volt pixels. So these only hit a maximum of around 9,000 lumens, and they started slightly brighter, slightly under as well at around 1,000. So these are not as bright as your 5 volters. So in terms of power consumption, they're using more in terms of wattage than your 5-volt pixels. So there is a loss here. You can see at the load around 10% that they're using pretty much more than double the amount of power to produce the light, and there's a steady path running pretty much in parallel with the 5-volters as they climb. So yeah, power consumption there isn't great. In terms of pixel efficiency, wow, we can see a massive starting lack of efficiency here, but it comes in fairly well on a curve there as the brightness increases. So once you've got down to about 40–50%, it's not as bad as it could be. They're still nowhere near as efficient as a 5-volt pixel, but you're gonna get a long way further with these. So if you're running a long string of, I don't know, maybe probably 400, I should think, on one of these strings at 30%, before you're going to need to power inject. So that's probably 4 times the number of pixels in a string. So you've got a trade-off. You've got ease of use. You can just sling 400 up of these and be done with, versus efficiency. I hate to say this, but probably if you're retired or you're working part-time and you've got plenty of time to play about with power injection, then 5-volt is looking positive. If you just want to get these up, done, happy days, then 24-volt is winning. But how is it doing on the thermal stakes? So thermal wise, actually these are pretty good. They're coming in at about 34 degrees C, so they are very thermally efficient. That's a whole 1 degree C up on the 5-volt. So yeah, I've no concerns about these on temperature. The only issue with them is that they're not quite as efficient, obviously, as a 5-volt. But how are they going to compare to the old daddies, the 12-volt resistor and the 12-volt regulator? We'll find out shortly. Next up, we have our 12-volt 4-wire that we looked in detail a bit more at a couple of weeks ago. If you haven't seen that video yet, I'm going to put the link to it up here. So 12-volt 4-wire suddenly make the 24-volt ones look a lot better, and the 5-volt ones really bright. The brightness levels of these, particularly at lower levels, isn't great, but it does increase rapidly once you get past about 40%. So you're going to have to run these at a higher brightness level to match up with your existing pixels if you're using them. So they took a little while to get going. Once they got onto the higher levels, the brightness increased rapidly. Now I was so unsure about these values that I actually did read these values and go through them a couple of times to make sure that I hadn't messed something up somewhere. So yeah, they are particularly low. I found no issues in my data. The 2 times that I ran it, it came out with the same values. Power utilization, this is where we see the results of the lower brightness, because these are undercutting even the 5-volt pixels in terms of power utilization. Now we've got a trade-off there between the fact that you're going to have to run these at 50%, say, to match a 30% of a 5-volt. But even at 50%, you can see that they're using around the same amount of power as 20% on a 5. Now if you want to sit and crunch this data yourself and see what you think to make up your own mind, I'm going to put a copy of all the data, all the numbers into a spreadsheet, and I'll put a link to that on a Google Drive. We'll link it below so that you can open it up and you can draw your own conclusions. So there we go. So 12-volt 4-wire, they're not as bright, but they are very efficient in terms of power utilization, and therefore you can run the brightness higher to compensate and still not kill yourself in terms of the power. So let's bring that in then, and there we go. We can see from the start that the 4 wires are really slow to get going, and that's because they hardly produce any light at 10%. But once you're up to 20, 30, then they're coming into line with the others. And if I knock out the first stages so that we can see how they're doing further down the line, we can see that actually they come in really well, and they're at the top end, they are nearly as efficient somehow as the 5-volt. I'm not sure how they're doing it. Again, it must be pulse width modulation because these are native 12 volts. So it's a 12-volt IC running the LED. So yeah, very, very poor efficiency at the start, but get them going up to 50-60% and they're really quite good. So in terms of thermal efficiency on these, amazingly, they undercut the 5-volters even, only very slightly. So really efficient. These new ICs that are coming out are really doing the biz. Using pulse width modulation to drive the LEDs instead of dragging the current down with an old-fashioned resistor or regulator is really thermally efficient, and is going to give a lot of peace of mind when you're putting them out on your house. Next up we have the 12-volt resistor pixel. Now these have been around nearly as long as the 5-volters and are certainly the most common pixel used in the hobby today. Being 12 volt, you can typically run about 200, 250 of them in a string, and happy days, off it goes. If you want to put more on a port, then you'd need to power inject, etc. But I don't personally like power injection these days. Ports are cheap compared to the old days, so I'm happily sticking 200 of these on a string. That's it, that's my port utilized onto the next one. So the 12 volts coming in on these is converted by a bank of resistors on the back, hence the name, and they drop the input voltage by around 7 volts down to the 5 volts needed by the IC and then onto the LED. Now the resistors have got one job. They're taking 7 volts out of your voltage, whether you've got 12 volts going in or whether you've got 10.5 going in. They're still going to consume your 7 volts. So you will see the colours start to fade slightly as you get in towards the end of the string. Now the way the resistors take the 7 volts, they typically would turn it into heat. So I'm not expecting great results on the thermal scores, but let's see how they're doing on lux. Now light-wise, they're pretty good. They're coming in second place here compared to the 5-volt pixels with a nice steady ramp there. They're starting a little dimmer than either the 24 volts or the 5 volts, and they've got a steady climb then, taking over from the 24s into second place all the way up to about 90%, where the 12 volt 4-wire take over and pip them into third at the 100% mark. In terms of power utilization, they start off reasonably well, just above the 12 volt 4-wire and just above the 5 volts at the beginning, but they've got a steady ramp as the power increases because these resistors are taking a set amount of voltage out, and as the watts are going up, the ramp is steadily increasing. So by the time you get to around 40%, these are number one in terms of the poorest efficiency. So after that, from 40% on, these are the least efficient that we've looked at so far. But they're cheap, they're cheerful, and that's why everybody loves them. Moving on to pixel efficiency, as we can see overall, the they start off in second place but end up in last place. If once again we get rid of the spurious data off the front caused by the 12-volt 4-wire, we can see that they're coming in last place. They are slightly less efficient than the 24 volts even. So there we go, cheap and cheerful, but you're paying for it in terms of efficiency. Now I'm expecting poor results on the thermal test, so let's have a look. And there we go. We can see that the maximum here is 41 degrees C. Now that is because these here resistors are busy doing their job, and they are converting power into heat, and therefore you can see it on the thermal image. And that's the way these are designed to work, so we expected them to be hotter. They go 40 degrees C, around 22 degrees C more than the ambient temperature in the room. Last up then, we have got our 12 volt regulated pixels. Now, these haven't had a great reputation in the last few years. Now, the problems caused with the regulated pixels was a poorly designed PCB, which led to power issues and which led to heat, and off it went. But the 12 volt regulated pixel isn't actually that bad as long as you get a good quality one. So where the resistor pixels were simply having 7 volts pulled out of them by the resistor bank, regardless of whether it was 12 volts going in or 10.5, the regulated pixels are a little more intelligent. So they'll be pulling the output to 5 volts, whether there's 12 volts going in and they need to pull 7 volts out, or whether there's 9 volts going in and they only need to pull 4 volts out. They're a little bit more intelligent, and so you're going to get uniform colours all the way through the string. Now, once again, these are going to be converting power into heat to achieve the voltage losses, so I'm not expecting great results on the thermals. But likewise, on the lux levels, we're really good on these. Let's see watts per pixel. Sadly, the voltage regulators like their juice. We have blown the others away in terms of power utilization and lack of efficiency, therefore, on these regulated pixels. So you're getting a uniform color, but you're paying the price in terms of power consumption. And if we skip through to the last one, let's bypass that one and jump to the, there we go, jump to the latter stages. We can see that these are the least efficient, bar none. They're coming in above even the 5 volt, they're coming in above even the 12 volt resistors as the worst performers in terms of efficiency. And I suspect now when we move on to the graph, yeah, 50.8 degrees C. So these are about 10 degrees C hotter than the resistors, which themselves were several degrees C hotter than the 24s, the 12s, or the 5 volts. So that's the end of the raw data there. Overall, what do we think? Well, 12 volt regulators if you need everything to look perfect, or you're going to have to use 5 volts and inject power really regularly, like every 50 pixels or so, to maintain that nice uniform look. I don't think anybody's got time for that. 12 volt resistor, they're the favourite. They get warm. They are not the most efficient, but you only have to inject every 200 or so, which makes them really popular. They're also relatively inexpensive. 4-wire, they are slightly more expensive. They have the resilience of the 4 wires, of course, the backup data line discussed in the other video. They are more efficient though than the 12-volt resistor, but you have to drive them hard to get the luminosity and therefore the brightness that you want. Once again, you're going to be looking at about 200 of these in a string before you have to power inject, or you just run strings of 200. 24 volts, I would guess that we're going to be looking at around 400, 450 pixels in a run before you'd need to power inject. I only have a string of 50 because that's all I was sent, so I can't prove that yet. But I look forward to getting some more when they go on general release in Q2, apparently, of 2025. So we'll watch this space and we'll see them launch. And I'm looking forward to these because it's going to be an interesting upgrade for the hobby. But you have to make sure that either you're running only data and ground out of your controller and separately feeding power, or you're running a board like the Baldric, which can take 24 volts. So just beware on your boards there. And last of all, 5 volts, the daddy of them all, as it were, the oldest in the bunch. Really good, really lovely luminosity levels, really good efficiency, but you've got to power inject somewhere between 50 and 100 pixels to maintain that, which a lot of people haven't got the time for, myself included. Much as I'd love the efficiency, I'd want to sit there creating power injection feeds and all that nonsense. So I have to be honest, at the moment most of my show is on 12 volt resistors, but I'm wondering if that's going to change to 24 as time goes on. So I hope you found that useful. That's a fairly in-depth one today. We need a more fun one next week, I think. So next week's going to be the return of the newbies guide, and we're going to be, having purchased some pixels, we're going to be connecting them up to a controller for the first time. We're going to be bringing in a power supply, getting that wired up, wiring the power supply to the controller, and getting some illumination in our pixels. So if you haven't done it already, hit subscribe below. Don't forget to hit like as well, subscribe, etc. If you found what we're doing useful, please do buy us a coffee or do a super thanks down below, because it really helps the channel. Whilst I was sent these 24 volt pixels, I have had to buy all this other stuff. So every little helps the channel, and it gives us the content that you guys are looking for. So thanks again, take care, see you on the next one.